Hello everybody, welcome back to another discussion dynamics. Today we will talk about work energy of rigid bodies. And plan for today is following. We will have a brief lecture review and then we will solve one example. Without further ado, let's dive straight into our discussion. Here is brief lecture review. So since we are in work energy chapter, we will just use work energy equation. Exactly the same one as we've seen earlier this semester. Work energy equation. T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. And this equation, or these 5 terms you can see in that equation, are almost exactly the same as those you already seen in this semester. There are just two caveats, right? And the goal of my brief lecture review is to just show you those two caveats. But before I show them, let me draw a drawing, okay? So let's imagine that we have a rigid body. This is our rigid body. And that rigid body has mass m and moment of inertia about its center of mass. And that center of mass is located, I don't know, maybe here. Why not? And what else do we know? We know following velocities. We know velocity of our center of mass. And we also know that our body rotates with omega. Let's also assume that our body is pinned at point A. So we will have a pin in here. Okay. And I think that with all of that information, we can finally write kinetic energy for our rigid body. And that kinetic energy is following. T is equal to 1/2 m Vc squared plus 1/2 Ic omega squared. And this is exactly the Koenig's theorem. This is kinetic energy of rigid body, or in some countries they call it Koenig's theorem. Okay. However, there is another way to calculate this energy, because every time you localize a pin in the system, like in our system, you can actually write such expression. T is equal to 1/2 AI omega squared, where IA is equal to IC plus MD squared, where D is this distance naturally. And this is parallel axis theorem. Or Stein's theorem. Yeah, so there are two ways to calculate kinetic energy. Please observe that this moment of inertia has nothing to do with this moment of inertia. There are two different moments of inertia, right? One of them is calculated about point A, the other one is calculated about point C. Okay, so there is first thing I want to cover in the lecture review. There's also another one. Potential energy of rigid body. So our potential energy will be mg times h, where h is just an elevation of center of mass. H is elevation of COM. So if I would like to put it on the drawing, so let's say that my datum is here, and that elevation will be basically here. Okay, guys, this is how we calculate kinetic and potential energies. Are there any questions? I don't see any, so let's use our new knowledge in solving example number 1. Here is example number 1. As usual, please take a couple of seconds to read and understand the problem statement before we start our solution. Okay, so what do we have in here? We have two bodies, right? We have a gear. And what do we know about it? We know that it has mass m, it has radius r, and it has moment of inertia about each center of mass, that is IB. And that center of mass is located at point B, here. What do we know about bar? We know very similar stuff. We know that bar has mass m, big M, length L, and moment of inertia about point D, which is its center of mass. What else do we know? We know that there is a friction force at the slider C, this slider. We know distance B. We know that our system, no, not our system, our bar starts with some angular velocity, omega 0 bar. And we also know that at configuration 2, system stops. System stops. And there is no slip basically here. There's no slip at that point. I mean, it's a gear, so there is no slip. Okay, and they ask us to find K. They ask us to find stiffness of that spring. So let's do it. I'm just going to write down this equation on the board. T1 plus V1 plus u-madison non-conservative is equal to T2 plus V2. And our goal is to just find these 5 quantities: T1, V1, T2, V2, and u-madison non-conservative. In the past, I was just writing them right away, right? I was just writing them in a column. T1, V1, T2, V2, and u-madison non-conservative. However, in this case, we will need some effort to find each of them. That's why we will just find them one at a time, okay? So let's just focus maybe on T2. Since our system stops at the end, can any of you tell me what is T2? 0. Perfect. 20% of the problem done already. And let me maybe copy this thing in here. Okay, so we are done with T2. Now let's focus on T1. So that T1 can be decoupled into T1 of bar and T1 of gear. Let's focus on T1 of the bar. And let's use Koenig's theorem to express it. So in here we will have 1/2 big M VD squared plus 1/2 ID bar omega 0 bar squared. Okay, can we calculate it right away? No, not yet. And by the way, we can also use it, use different expression to find it, because I think that there is a pin in the system. Point A is a pin. So we can actually calculate our T1 bar as 1/2 IA bar omega 0 bar squared. Let's do it in two ways, okay? I will show you how to do it in two ways, and hopefully we will end up with the same answer, okay? So let's focus on the first expression. I think that we do not know VD. Yeah, we must find VD. So, question to you guys, just by looking at this picture, can you please tell me what is the expression for VD? What is the velocity of this point? Exactly, yeah. No worries. Exactly, you're right. It's omega 0 bar times L12. Okay, let's find it. So omega is what? Omega is 1 plus, times 2 divided by 2. Okay, it will be 1 meter per second. Okay, so let's plug in values. We have here 1/2 times 2 times 1 squared plus 1/2 times 2 times 1 squared. Okay, that's funny. Okay, so this will be just 2 joules. Okay, how about the other version of our expression? We don't know this guy. We don't know IA bar, so we must use parallel axis theorem to find it. IA bar will be ID bar plus big M times some distance square, and that distance will be L12, because this is the distance between A and D, so I can put L12 in here. Okay, let's find that as well. So this will be 2 plus 2 times 2 divided by 2. So this is 4 kilograms meter squared. Let's plug in values. 1/2 times 4 times 1 squared. As you can see, it's again 2 joules. Okay, so our theory works. You can calculate kinetic energy using these two expressions, and you should end up with the same answers. Are there any questions before we move forward? We're good. Okay, so let's find T1 gear. So in here we will just write 1/2 mvb squared plus 1/2 ib gear omega 0 gear squared. Okay, I am afraid that we don't know two variables here. We don't know VB, and we also don't know omega 0 gear. So again, question to you guys. Can any of you tell me what is VB at the time instant 0? Or in configuration 0, sorry. What is the velocity of this point? omega 0 bar times L. So this would be 1 times 2. This would be 2 meters per second. Okay, so we're done with this guy. And now omega 0 gear. So I think that we can find omega 0 gear if we express VB in a different way. So VB can also be expressed as omega 0 gear times R, I believe. Because you guys can see that that point, let's call it E maybe, that point has 0 velocity. So that's why our VB can be expressed with such expression. So in here you can see that our omega 0 gear is VB divided by R, which will be 2 divided by 1, and this is 2 radians per second. Cool. Okay, we know everything, so let's plug in values, and let's see what will happen. 1/2 times 1 times 2 squared plus 1/2 times 1/2 times 2 squared. And this should be 3 joules. Okay, so I think that we found T1. Because T1 is equal to that. So that means that this will be 2 plus 3, and this is 5. Okay, so T1 at the beginning is 5. So yeah, we have 40% of the problem done. Now let's focus on potential energies, okay? So now let's do V1. And let me copy that drawing. I like to have a drawing in my screen. Okay, so we have V1. Okay, and our V1 can be divided into V1 gravitational, so V1 grav plus V1 spring. Okay, let's find V1 grav. But before doing that, I must introduce the datum, right? So I want to introduce my datum here. Okay, another question to you. What is the potential energy of our system at the beginning? It exactly is 0, because all the COMs are aligned with our datum. How about spring? They told us that spring is undeformed in configuration 1. They told us that. That means that potential energy of that spring is 0. Okay, so our V1 is 0. 60% of the problem done. Now V2. V2 can be expressed in a similar way. V2 gravitational plus V2 stiff, coming from stiffness. V2 spring. Okay, so V2 grav will not be 0, yes, because our COMs are below the datum. So in here I have to write mg times some elevation plus little mg times some elevation. Okay, guys, again, question to you. What should I put in this bracket? This is elevation of center of mass of bar. Anybody?
Yeah, negative L over 2.
Perfect. It's negative L over 2. And the other one will be negative L. Okay, and if you plug in values and grab your calculators, you will end up with the following value here. Oh, sorry. Oh, no, it's okay. For 49.05 joules. And now stiffness, so V2 spring. The expression for here is 1/2 K times some angle squared. For the fifth time, I want to ask you, what should I put in this bracket? What angle I should put in that bracket? Or what is the deformation of the spring? Divided by 2? No, multiplied by 2, yeah. It's pi over 2. It's 90 degrees. It's 90 degrees. Yeah, the deformation of the spring is 90 degrees, so it will be pi over 2. And if you plug in values here and grab your calculators, you'll end up with a funny number, because it will be 1, 2, 3, 4. And a dot in here. K. Okay, and K is not known. So in here, our V2 spring is 1.234 K. And that's all, right? Because our V2 is basically minus 49.05 plus 1.234 K. Okay, I don't know what you think, but I think that 80% of the problem is done. So now let's do the remaining 20%. So we did that, and now we must focus on the work of non-conservative forces. I want to steal that drawing. I want to put it here. Okay, but before we calculate work of non-conservative forces, I think we should first show what non-conservative forces act on our system, right? So we should start with showing all non-conservative forces acting on the system. Acting on our system. Okay, so let me draw it. I will draw it in arbitrary configuration. So let's say that our bar will look like that. Our bar is pinned at point A. This will be point C. Maybe our disk is here. And this is our gear. Okay, so this point will be point B, and this point will be point E. Okay, guys, so what non-conservative forces act on our system? I think that there is reaction force at A. Yeah, our A is spin. So there will be like such reaction here. I also think that we will have like some reaction force between those teeth of the gear, right? So in here we will have some normal force. In here we will have some tangential force. But instead of drawing these two components, I will just call that force as R. I don't know. R acts in this direction. I don't know the direction. Okay, so I have two right now on the board. Is there any other non-conservative force acting on our system? Yes, exactly. There's a friction at point C. So it will be here. And since our brake pad moves that way, so our friction will be pointing this way. Okay, guys, that's all. I think there are no other non-conservative forces. So we can just write down such expression. U12 non-conservative is equal to U12 of A plus U12 of R plus U12 of friction. Okay, let's express it in more mathematical way. So this will be an integral from some point A to some point B, A times displacement of point A plus integral of R times the displacement of point E, right? Because our force R acts on point E, plus some integral from A to B of friction times the displacement of point C. Wow, so we must integrate these three integrals in order to find our work. Let's do it quickly. Okay, guys, can you please tell me what is the value of displacement at point A? I just would like to remind you that point A is a pin. So what is DSA? It is 0. Point A does not move anywhere, right? So that integral was easy to calculate. Okay, I also would like to remind you that there is no slip at point E. Can any of you tell me what is the instantaneous displacement at point E? It is 0, yeah. There is no slip. Our disk rolls on the ground, so this one will also be 0. Which means that these two integrals will also be 0. Okay, however, I think that DSC is not 0. The displacement is not 0. If this is the trajectory, of point C, I think that DSC will be pointing this way. So unfortunately, we have to calculate the third integral. So in here we will have integral of minus f dsc, and I think I would like to, for the final time today, I would like to ask one of you to tell me what are the integration bounds here and here. Just a hint, our point C travels from here to here. Anybody? Almost good. So John said that this is from 0 to pi over 2, but these are not angles. John, what I'm asking you, I would like to tell me what is the length of this arc length. What is that arc length? Well, oh. Perfecto. Exactly. It's b times pi over 2. Yeah, I needed a distance. Yeah, didn't need the angle. Yeah, awesome. So arc length is b times pi over 2. Awesome. And I think that f is constant because they told us that f is constant. So calculating that integral will be super simple. So our u12 non-conservative is equal to minus f b pi over 2. Let's plug in values. It will be minus 10. I forgot what b was. Let me scroll up the board. What was b? 1 meter. b is 1 meter. 10 times 1 times pi over 2. So this is exactly minus 5 pi joules. Okay, and it seems to me that all the problem is solved, right? Because we found these 5 expressions. So let us plug them into our original equation. So in here I will just write T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. Okay, what was T1? I think it was 5 joules. So 5 in here. V1 was 0. U12 we just found, so it's minus 5 pi. T2 is 0 because the system starts at the end. The system stops in the end. And V2 V2 was that funny expression, right? V2 was minus 49.05 plus 1234 K. Okay, one equation, one unknown, let's find K. K is equal to 1 divided by 1.234, 5 minus 5 pi plus 49.05. Okay, grab your calculators and find that K is approximately 31.071 newtonometers per radian. And this is the answer. Okay, that's all I've got. That's all I prepared for today. So thank you for today and have a nice weekend.